we are going to discuss here category of runoff estimation methods known as empirical formula. We will understand in this session when they are used, why they are needed, and we will look into the most well-known empirical formula, Berkeley-Ziegler formula. Now, first you look at the slide. A rational formula is used only when the area draining water into the sewer is small. You can tell that smaller than 400 hectares. You may recall the rational method which we have discussed earlier, that is Q is equal to CIA. It is simple as well as theoretically it is sound, but it has a limitation. The rational method assumes that the entire catchment area contributes runoff simultaneously at the outlet after a time equal to time of concentration. For this assumption to hold it true, the catchment must be small as it is less than 400 hectares. Why we are taking 400 hectares means that's approximately 4 square kilometers or about 1.5 square miles. Beyond this, two problems we have. The first problem is the rainfall intensity, that is Ri, is no longer uniform across the entire area. It may be raining heavily on one side of the catchment while the other side remains dry. The second problem is the runoff coefficient, that is C, or impermeability factor, becomes extremely difficult to determine accurately for a large heterogeneous area with mixed land types, varying soil types, and different slopes. For these reasons, when the catchment area exceeds 400 hectares, usually we will move towards the empirical formula. An empirical formula is derived from the observation and experience, not from the theoretical principles, but it considers the theoretical principles to a certain extent. Engineers and hydrologists collected years of actual runoff measurements from the real catchments, analyzed the data, and then fitted mathematical equation to match the observed patterns. The empirical formula is applicable and under certain specific conditions. In other words, they are local in nature and should be used only when certain specific conditions are fulfilled. This is extremely important. Unlike rational method, which has universal theoretical validity, the empirical formula are local. A formula developed for Swiss mountains catchments may not work for a flat agricultural land in India. A formula developed for American urban areas may not work for the tropical rainforest regions. You should always check the conditions under which a particular empirical formula was derived before we are using that empirical formula. Here, the variable A usually it will be denoted by catchment area in hectares, whereas that Ra is the rainfall intensity in mm per hour over the entire area. The relative imperviousness is similar to runoff coefficient, where S is the slope of ground in meters per 1000 meters length. This is the earliest form of empirical formula, originally given by a Swiss engineer for local conditions, but later widely adopted in the USA. The Berkeley-Ziegler formula has an interesting history. As I told, it was developed by the Swiss engineers named Berkeley Ziegler for catchments in Switzerland, a country which is known for its mountainous terrain, steep slopes, and specific alpine rainfall patterns. Later, engineers in the United States found this formula useful for certain applications and adopted it. However, remembering the warning, just because it was adopted in the USA does not it can be used in the other parts of the globe also. But it still carries the characteristics of the Swiss catchment area. Here you have that equation Q is equal to 296 CRI A S divided by A to the whole power 1 by 4. Now I will break down every single component, that is Q is the runoff, that is units is liters per second. This is the peak discharge which we are calculating. The 296, it is a constant. This is a dimensional constant that makes the equation work when the area is in hectares. Rainfall is in mm per hour and the slope is in meters per 1000 meters. It do not change this number unless you are changing the unit system. Where C is the surface constant, it represents the nature of the ground surface or relative imperviousness. That is, range is 0.5 to 0.9, where average recommended value is 0.7. Now we will have how we select the C is equal to 0.5, that is for the permeable surfaces, sandy soils, gentle slopes, vegetated catchments, and the grassland. Where C is equal to 0.7, it can be used in the average and mixed conditions. It may be in the some impervious as well as in the some pervious. Whereas we are having C is equal to 0.9, which can be used in the high impervious surfaces, clay soils, steep slopes, and dense urban areas. Whereas we are having Ri is the rainfall intensity. This is given by the units mm per hour. This is the maximum rate of rainfall over the entire catchment. For larger areas, you may need to use an average or design storm value, whereas the A, it is given in the that is the catchment area where that units is given in hectares. Remember, 1 hectare is equal to 10,000 square meters, which will be equal to the 0.01 square kilometers. Now, next we are moving into the slope, that is at S. Here we are having that units. The units is in the meters per 1000 meters. This is a dimensionless ratio in effect. For example, if a ground drops 5 meters over a distance of 1000 meters, then we will have S is equal to 5. If the ground drops 20 meters over 1000 meters, then we will have S is equal to 20. That is a steeper slope. So that we are having S divided by A to the whole power 1 divided by 4. This is the fourth root of S divided by A. Notice that slope S is in the numerator and A is in the denominator. Rising to the power of 1 by 4, it is the same as taking the fourth root. Here you will have that important observation, because area A appears in the denominator inside the fourth root. Larger catchments produce a smaller contribution from the slope factor. This makes physical sense. On a very large basin, the overall slope effect gets diluted. Let me help you understand what this formula is telling us. Here, the Q increases when C increases because the increase in C can be related to the more impervious surface. Whereas the Ri increases denotes the heavier rainfall. Whereas the A increases will tells you the larger catchment. Whereas that S increases will gives you the steeper slopes. The Q decreases when A is very large because A appears in the denominator inside the fourth root. The fourth root term is the distinct feature of this formula. Most other formula treat slope linearly or with a square root. The Berkeley-Ziegler used a fourth root, which means that slope has a relatively weak influence on runoff compared to area and rainfall intensity. Let me very clear about the limitations of the Berkeley-Ziegler formula. Here you are having the local applicability. This formula was developed especially for the Swiss conditions. It may not be accurate for flat terrains, tropical climates with different rainfall patterns, arid or semi-arid regions, whereas the catchments with the very irregular shapes. Now you look at that area range. While this formula is intended for areas larger than 400 hectares, it may have its own upper limit. For extremely large basins, that is for thousands of hectares, more sophisticated methods like unit hydrograph or flood routing are needed. Next, we look into the single rainfall intensity, that is which has been given as Ri. This formula uses one Ri value for the entire catchment, ignoring the spatial variation in the rainfall. Now, average slope only. Here, the formula uses a single average slope, yes. For catchments with highly variable topography, this may not be representative. And no time component. Unlike the traditional method, this formula does not explicitly include the time of concentration. It is essentially a steady state formula. Also for a narrow range, the coefficient C ranges only from 0.5 to 0.9, which may not capture the full range of the surface conditions which is found in nature. We discussed the Berkeley-Ziegler formula now, which is one of the earliest formula for runoff estimation. Now in this slide, we will continue our discussion of empirical formula and we examine the Metcalfe's formula, Metcalfe and Eddy's formula also. Before we look into the formula, I would like to discuss that. We learned that the rational methods work well for catchments smaller than 400 hectares. For larger areas, we turn this to empirical formula, that is equations derived from actual field observations rather than the theoretical principles. However, and this cannot be stressed enough, empirical formulas are local in nature. Each formula was developed for a specific geographic and climatic conditions. Using a formula outside its intended conditions can also lead to the error during the calculation. With this note, now let us discuss the Metcalfe's formula. Look at the equation on the slide. Here they have given Q is equal to 292 CRI into A to the S divided by A to the whole power 1 by 5. This formula was devised for local conditions of St. Louis in USA. You know that St. Louis is a major city in the Midwestern United States, located along the Mississippi River. The formula was developed specifically for the hydrological and climatic conditions of the region. This means the constant particularly the number 292 and the 1/5 exponent were calibrated using actual runoff measurements from the St. Louis catchments. Here also you will notice that McMahon's formula looks very similar to Berkeley-Ziegler formula, which we have studied earlier. Now we will have the comparison of the two formula. The Berkeley-Ziegler formula have a constant of 296, whereas the McMahon formula have a constant of 292. The exponent of the Berkeley-Ziegler formula is 1/4, fourth root, whereas the McMahon's formula is 1/5, that is a fifth root. Both formula have the same basic nature. Q equals a constant multiplied by C Ri A and then S divided by A raised to some fractional power. Both there are two key differences. The first difference is constant. The Berkeley-Ziegler uses 296, whereas the McMahon uses 292. These are all very close numerically, but they reflect different calibration data sets. The second difference is the exponent. This is the most significant difference. The Berkeley-Ziegler formula rises S divided by A to the power 1/4, whereas the McMahon rises S divided by A to the power 1/5. Now understand that fifth root. What does this fifth root mean? A fifth root is even a weaker influence than the fourth root. Okay. Now I will give an example. You are having, suppose, S divided by A is equal to 32. If you put the 32 to the power to the whole power 1 divided by 4, approximately you will get a value around 2.4. Whereas if you put the same root to the 32, that approximately the value, and the exponent becomes smaller, that is from 1/4 to 1/5. The slope and the area term has less influence on the final runoff value. In McMahon's formula, the effect of the slope is even more diluted than the Berkeley-Ziegler formula. Now, next we are moving into the coefficient C. The value of C may vary between 0.3 to 0.9, though an average value of 0.75 is recommended. Now you notice the two things here. The McMahon's formula allows for lower minimum value, C value of 0.3. This suggests that St. Louis catchment used for calibration included some highly permeable surfaces, perhaps sandy soils, forest, grasslands, or agricultural land, where runoff is only 30%, where runoff is 30% of the rainfall. Second, the recommended average value of 0.75 is slightly higher than the Berkeley-Ziegler 0.7. This indicates that typical St. Louis catchments might be somewhat more impervious than the catchments which is used for the original formula. Now, let me give you a practical guidance for selecting the C in McMahon's formula. We will select C is equal to 0.3 to 0.4 for the highly permeable surfaces, sandy soils, flat terrain, dense and the dense forest. And we will have select C is equal to 0.5 to 0.6 if the mixed conditions with the significant pervious areas, loamy soils and the gentle slopes. Now we will select C is equal to 0.7 to 0.8 for the urban residential areas, clay soils, moderate slopes and commercial development. Now we will select C is equal to 0.9 for the dense urban areas, fully paved surfaces, steep slopes and the industrial zones. If you have no specific data, use the recommended average of 0.75 for C. Now next we are moving into the Metcalfe's and the ND formula. Now you look at that equation equal to 48.32 to the 35,000 divided by 2.47a plus 125 plus 50. Now, the above formula contains only the expression for catchment area. This is the critical point. Unless the previous two formula, Metcalfe and Eddy's formula does not include rainfall intensity, slope of the ground, as well as surface coefficient or that C value imperviousness. The only variable in this formula is A. That means the catchment area in hectares. You might be wondering, how can a runoff formula ignore the rainfall intensity? Because there is reason for that. This formula was developed for specific conditions where rainfall intensity and slope were relatively constant across the region of the study. Under those particular conditions, the only major variable affecting runoff was the size of the catchment area. However, and this is extremely important, you must understand the limitations of this formula also. By excluding rainfall intensity, the formula implicitly assumes that same design sum for all catchments. By excluding the slope, it assumes all catchments have the similar topography. By excluding the surface coefficient C, it assumes all surfaces have similar imperviousness. Therefore, Metcalfe and Eddy's formulas should be used with the where only the project conditions closely match with the original study conditions. For very large catchments, the peak runoff per unit area decreases because rainfall is rarely uniform across the entire area. Different parts of the catchment contribute runoff at different times. The channel storage attenuates the flood wave. So despite its simplicity, Metcalfe's and Eddy's formula is not considering these factors. The above three formula give satisfactory results only when the catchment area is of limiting size, that is says, which we have discussed already. Now, beyond the 800 hectares, several problems occurs, that is the non-uniformity in the rainfall. It becomes increasingly unlikely the entire catchment experiences the same rainfall intensity at the same time. That is, next one is the long time concentration. The time for water to travel from the farthest point to the outlet becomes very long, often exceeding the duration of typical short duration storms. And next is the channel storage and the flood wave attenuation. As water travels through long channels, the peak flow gets reduced due to storage effects. These formulas do not account for this. And a single slope value S and a single coefficient C becomes the less representation of the highly heterogeneous large catchments. We are going to look into the next Fanning's formula. Here we are having Fanning's formula is equal to Q is equal to 3125 A to the power A K to the power 5 by 8, where AK is the area in square kilometer. Here AK is the catchment area in square kilometer. Notice that exponent 1 by 8. This is the 8th root. This means that runoff increases very slowly as the area increases. Fanning's formula is suitable for large river basins. This equation, the equation next is Q is equal to 87,000 A K to the power 1 by 4. which is referred to as the Talbot's formula. This uses a fourth root, the same exponent used in the Berkeley-Ziegler formula. Talbot's formula gives higher runoff values compared to Fanning's for the same area. Both of these are generally empirical formula, but now let us move to the formula that are more relevant for the Indian conditions here. Now, next we are looking into that formula. Rives formula. The constant C, the value of constant C may vary between 450 to 625. Unlike the previous formula, that is Dickens formula, the Rives formula has three distinct ranges here, which is C is equal to 450 for the flat, whereas C is equal to 625 for the steep. Here you can notice that exponent 1 by 3, that is a cubic root. This is difference from the Dickens formula, which we are going to discuss, which give more weight to the area compared to the Dickens formula here. Now, the Dickens formula is Q is equal to 14 C A K to the power 3 by 4 here. Now, the value of C changes depending on the size of the catchment and the rainfall. The C will be used as 250 for very large areas, whereas the C will be used for 850 where the areas of average size, where the average rainfall is between 600 to 1200 mm. And that C will be used for 1600 for the very small areas. What does this mean? The smaller areas tends to have higher runoff per unit area, so C is larger. Larger areas have more storage and attenuation. Now, next we are moving into the English formula, that is the final formula. Here we have Q is equal to 123100 AK divided by square root of to the whole AK plus 10.4 here. Now, it is not a simple powers like that others. The area AK appears both in the numerator and inside the square root in the denominator. As area increases, the denominator also increases. So the runoff does not grow linearly. Now we will move to the concept reclaimed water. Reclaimed water, also known as the recycled water or water reuse, which refers to wastewater that has been treated so that it can be safely used again. Now, where we are getting that wastewater, primarily it comes from the municipal sewage, which is domestic wastewater from households, and industrial water, which will be generated from the various industries. So instead of disposing this wastewater after a single use, we treat it and reuse it for the various purpose. It is very important to understand the main purpose of the reclaimed water is reuse. It's not the disposal. So traditionally, wastewater has been treated and then discharged into rivers or oceans. But with the reclaimed water, we will have the another view also, from waste disposal to the resource recovery. Now look at the key point. Reclaimed water is usually not meant for drinking purposes unless it undergoes advanced treatment process. Instead, it is commonly used for irrigation, industrial cooling, landscaping, and the groundwater recharge also. This makes very practical and efficient resource. Let's now look at why reclaimed water is so important through the significance of the reclaimed water. First, it helps in conserving the fresh water. Freshwater sources like rivers, lakes, and groundwaters are limited. By reusing the treated wastewater, we reduce the pressure of the natural sources. Secondly, the reclaimed water ensures a reliable water supply, especially in the during drought conditions. Even when rainfall is low, wastewater generation continues. So, reclaimed water acts as a consistent and dependable resource. Third, it helps in reducing the pollution. If it is untreated or partially treated, wastewater is discharged into water bodies. It can harm that aquatic life and degrade the water quality also. By reclaiming water, we minimize pollution in rivers, lakes, and oceans. Next, it plays a major role in sustainable water management. It promotes a circular approach where water is reused rather than simply being it is wasted, aligning with the sustainability principles. Finally, reclaimed water helps meet growing the demand caused by population growth, urbanization, and industrial development. As cities expand, water demand increases and reclaimed water becomes a crucial solution. Now we will look into the treatment process of the reclaimed water. Now, the treatment of reclaimed water is carried out in different stages, and the level of treatment depends upon the intended use of the water. For example, water used for irrigation may need less treatment, but water intended for industrial reuse or indirect potable use requires more advanced treatment. So let us go step by step through the treatment process. First, we have primary treatment. This is the initial stage where the focus is on removing large solids and suspended particles from wastewater. It mainly involves screening, where large particles such as plastics and debris are removed, and sedimentation, where heavier particles settle down at the bottom as a sludge. This stage is physical in nature and it helps in reducing the load on the next stages of the treatment. Next comes the secondary treatment. Here, microorganisms such as bacteria are used to break down the organic matter present in the water. In this stage, the dissolved and the biodegradable pollutants are significantly reduced. Organic waste is converted into simpler and the stable substances. This process is very important because it removes the major portion of the pollution in the wastewater. The common example includes here activated sludge process and the trickling filters. Now, next we are moving into the advanced or the tertiary treatment. This stage is used when high quality water is required for reuse. It includes advanced process such as filtration to remove the fine particles, nutrient removal, especially nitrogen and phosphorus, disinfection to remove the harmful microorganisms. In more advanced systems, the technologies like membrane filtration and reverse osmosis are used to achieve very high quality water. This treated water can be safely used for industrial applications and landscaping, and even indirect portable reuse in some cases. Now, we are going to look into the uses of the reclaimed water. As freshwater resources become scarcer and demand continues to rise, reclaiming and reusing wastewater is no longer just it is an option. It becomes a necessity. Reclaimed water, also known as recycled water or treated wastewater, can be safely used for many purposes, provided it is treated to the appropriate quality level. The first category is urban and municipal uses. These are the applications within the cities and the towns. Irrigation of parks, gardens, lawns, and the sports field. This is the most common uses of the reclaimed water. Think about all the green spaces in a city, public parks, decorative gardens, residential lawns, and the golf courses and the sports stadiums. These areas requires large volume of water, especially during the dry season. Using reclaimed water for irrigation saves precious drinking water for more critical needs. Next is the toilet flushing in buildings. The toilet flushing consumes a significant amount of water in commercial buildings, hotels, airports, and even residential complexes also. And next is the street cleaning and the dust control. Municipalities often use water trucks to clean streets and control dust on unpaved roads. These activities do not require high quality drinking water. The reclaimed water works perfectly for this cause. Next is firefighting. This is also the another practical application. We rarely think about it. Firefighting uses enormous amount of water. Reclaimed water can be stored in dedicated reservoirs or hydrant systems such as firefighting, which prevents a freshwater supply for other uses. The second category is agricultural uses. It will be used for irrigation of crops and nurseries. Agriculture is a larger consumer of freshwater globally, often accounting for 70 to 80% of the total water which is used. Reclaimed water can be used to irrigate a wide variety of crops, including food crops that are processed or cooked before consumptions, nurseries growing flowers and ornamental plants also. It reduces the dependence on freshwater for farming. This is a key benefit. When farmers use reclaimed water, they reduce their demands on rivers, lakes, and the groundwater. This leaves more freshwater available for drinking, domestic use, and environmental flows. In water scarce region, this can be practiced for sustainable agricultural. So agricultural use of reclaimed water supports food production while conserving the natural water resources. The third category is the industrial uses. This can be used as cooling water in power plants, industrial process water, equipments washing. Also, it can be used for the construction activities also. And regarding that environment, the final category is the environmental uses. This is most ecologically significant category. This can be used as well as the groundwater recharge. Groundwater levels are falling rapidly in many parts of the world due to over extraction. The reclaimed water, after advanced treatment, it can be deliberately recharged into the aquifers, which is referred to as the managed aquifer recharge. The water percolates through the soil, which provides additional natural treatment, and then becomes a part of the groundwater resource that can be extracted later for various uses. And this can be used for the wetland restoration. The wetlands are the most productive ecosystems on Earth, but many have been degraded or destroyed. The reclaimed water can be used to restore and maintain these wetlands. The water provides the necessary hydrology to support the wetland plants, birds, fish, and other wildlife. There are many successful complexes of constructed wetlands that uses the reclaimed water to create the new habitats and for maintaining the stream flows also. In many rivers, excessive water withdrawals have reduced stream flows, especially during the dry season. Low flows harms the aquatic life and concentrate pollutants. Reclaimed water can be released into streams to maintain a minimum environmental flow, keeping the river healthy and supporting fish and other aquatic organisms. Now we are going to discuss the topic that is environmental policy and legislation. Now, while engineers design treatment plans and control technologies, it is environmental policies to create the rules, incentives, and legal frameworks that drive the environmental protection. understanding this policy is essential for any environmental professional. Let's begin. Look at the definition of the slide. Environmental policy refers to the set of principles, intentions, and strategies adopted by a government or organization to manage the human activities with a view to prevent, reduce, or mitigate harmful effects on nature and natural resources. Now, this environmental policy is a solution. It is a government or that organization which intends to do about such problems. It includes the principles. That means principles means the core beliefs that guide action, such as nature should be protected for future generations, and intentions. Okay, what the government or the organizations or the agencies to achieve, such reduce river pollution of 50% in next 5 years, as well as the strategies. The specific plans and actions to achieve those intentions, such as require all factory to install effluent treatment plants. That is a strategy. Okay. So the environmental policy bridges the gap between recognizing an environmental problem and actually solving it. The key goals of the environmental policy is to protect the air, water, as well as the soil quality. This is most direct goal. That means how much sulfur dioxide can be released from a power plant, how much biochemical oxygen demand or BOD present in freshwater can be discharged into river, and how much heavy metal can be present in soil, present in the soil. So these are the things. Okay. These standards are based on scientific research about what levels are safe for human health and the environment. The second is to conserve biodiversity and ecosystems. The biodiversity means the variety of life on Earth, from the microscopic bacteria to giant whales. It covers everything. So that ecosystems are the communities of living organisms which interacting with their physical environment. So these environmental policies protects biodiversity by creating national parks and wildlife sanctuaries, protecting the endangered species, and preserving critical habitats like wetlands, coral reefs, and old growth forests. And the third goal is to promote that sustainable development, which balancing sustainable development is balancing the three things: economic development, social societal development, and environmental potential protection also. And the third goal is to regulate the pollution and resource use. This goal focuses on control and management. The policy set limits on how much pollution can be released, what technologies must be used, how much resource can be extracted. So this is about that key goals of that environment policies. Here we are having the three principles that form the foundation of many environmental policies around the world. The first one is the polluters pay principle. Okay, this principle states that any industries which is responsible for producing pollution should bear the cost of managing it. That is that. And next one is that precautionary principle. The precautionary principle state that if an action or policy has a potential to cause serious or irreversible harm to the environment or human health, lack of full scientific certainty should not be used as a reason to postpone that action. Okay. So this is and the third one is that sustainable development principle. This we have discussed a little bit in that earlier. The sustainable development principle recognizes that environmental protection, economic development, and the social development, which these three are interconnected, and this must be pursued together. So this is about that. Next, we look into that environmental legislation and institutional framework in India. This environmental legislation is refers to the collection of laws and regulations which has been enacted by governments to control human impact on the environment. The main purpose is to set legal limits on pollutions and to penalize the environmental violations and to provide guidelines for environment impact assessment as well as to protect the natural resources. Now we have the certain institutional framework in India. This mainly that for the first you look into the Ministry of Environment, Forest and Climate Change. This main function includes policy formulation. That means drafting any new environment policies and laws and implementation, overseeing the execution of natural environmental programs and for approvals, granting environmental clearances for the major projects and international negotiations representing India in global environment agreements like the Paris climate got like this thing. So and the next one is that Central Pollution Control Board. These will regulate the air and water pollution across the country, setting the national standards for pollution emissions and the discharges, monitoring the environmental quality through a network of sampling locations, providing technical guidance to the industry institutions or organizations or the agencies, as well as conducting research and publishing the data. And that next third one is that state pollution control boards. The central pollution control boards operates at the national level. State control boards works at the state level. There is one state pollution control board each state. For example, Tamil Nadu pollution control board and Maharashtra pollution control board. Like that, it will be existing for state wise. Mainly, their functions includes implementing the laws at that state level and conducting inspections of industrial units and monitoring ambient environment quality. And that third agency is a National Green Tribunal. The National Green Tribunal is a specialized legal body which has been established in 2000 for speedy environment justice. So these key features of this National Green Tribunal, it handled the cases related to the just Forest Act and the Environmental Protection Act. And here that it will have the fast decision. The National Grid will have fast decision. So this is the thing. These are all the important environmental laws in India. Environmental Protection Act, Water Protection Act, which has been formed in 1974, and Air Act, so control of Wildlife Protection Act, which is in 1972, Forest Conservation Act, which has been 1980. So National Green Tribunal has been formed in 2010. And next, we are moving into the key environmental policies in India. If we look at the specific policies, let me difference between the law and the policies. The law is legally binding. If you break it, you may be fines like that. Yeah, policy is a statement of principles and the strategies where everyone has to follow. So you think in this way, the policy is the roadmap. Legislation is the traffic police that enforces the rules on the road. So there is a difference. Now let us look at the four key environmental policies of India. The first one is the first one. We start with the national environmental policy. This will mainly guiding the document for sustainable development. Also, this national environmental policies focuses on the environmental impact, environmental impact assessment, as well as it focuses on the conservation uh, and public participation also. The national water policies, which has been formed by the year 2012, which is mainly deals about the sustainable water uses and that conservation and how the priority of water should be given for which activities, whether the first it is to be used for the domestic agriculture industry, like that the priority. Also, it promotes an integrated water resources management. And the next one is that national forest policy, which has been formed in 1988. We know that one third of the land area to be under forest cover. This states that also it involves communities in the forest management. Whereas the national and the biodiversity action plan mainly focus towards oriented towards the conservation and sustainable use of the biodiversity. With this, we are ending the module one. In this module one, we have discussed about the different aspects. That is that about the water demand, the water quality. We have discussed water quantity and how it the initial way how it can be treated and what are the environmental laws and policy existing in India. These are the things we have discussed in the module one. Thank you.